Our IWCS webinar series event is hosted by the Cable and Connectivity Industry Forum. We are certainly looking forward to being together again in person in Providence, Rhode Island, October 10th through the 13th, and we hope that many of you will participate with us again this year after 2 years of virtual conferencing. So today we welcome Thomas Meyer, the Fire Performance Lab Manager for Corning Optical Communications in Berlin, Germany. Thomas will be presenting his paper on the impact of the burner flame shape on cable burn performance testing, according to EN 50299. Thomas received his degree in mechanical engineering from the University of Applied Sciences in Dresden. He has more than 25 years experience in the field of fiber optics in varying engineering roles, such as applications engineer manager and research and development engineering process engineer. In 2016, Thomas joined Corning's materials group of the technology department as manager of the Fire Performance Laboratory. So with that, we certainly welcome and appreciate Thomas being with us today to present at today's IWCS webinar series event. So Thomas?
Yep. Thanks, David. Yeah, hello to everybody. You see my screen? I hope so.
Yes, I can see it well. Thank you.
Good. Hello, good morning and good evening to everybody. Thanks a lot, Dave, for the nice introduction. Today, I would like to share with you the results of our investigation about the impact of the burner flame shape on the burn performance testing. On the agenda, that I would give you a brief background about the execution of the burn testing according to EN 50399. Then I will talk about the method for the characterization of the flame shape. I want to give examples for flame shape variations. As a next, I will talk about the parameter setting that could influence the flame shape, as well as the flame spread, today with a focus on the burner design and the burner gas mixture. I would like to show examples of flame shape we have reproduced in our laboratory and the outcome. And I want to talk about the monitoring and the output. Finally, coming to the conclusion and the outlook. Since July 2017, all cables to be permanently installed in the construction works in Europe must be tested for thorough performance in case of fire and classified according to the European Construction Products Regulation, which is CPR. The corresponding CPR classes of cable are mainly determined by the EN 50399 test method. The test method itself imposes high requirements on test laboratories in order to obtain comparable results. While execution of the CPR, it became more and more obvious that the burn test results, in particular the vertical flame spread, can vary between laboratories. The picture in the middle should briefly explain the flame spread. The vertical flame spread is the extent of the cable damage measured on the cable combustion pattern, which is the distance between the burner center line and the tip of the combustion pattern. With the European Cable Association Europa cable, studies on the repeatability as well as the reproducibility of the test method and test results were carried out by round-robin testing over the years. The burn results showed a variation of up to 2 CPR classes at the same cable type in different labs. The EN 50399 has been revised and further requirements have been added based on experience since practicing CPR and the studies. The second edition of EN 50399 recommend to use a reference cable for proving the functionality of test method. I want to mention that the same reference cable is used for all investigation that we have made. Furthermore, the characterization of the flame shape is added in the new standard. It was found that also the flame shape of the burner can influence the test results. The new edition has been concluded in July this year, and the publication is expected by end of the year. So, how is a flame shape described? The flame shape describes the profile of a burner flame, which is projected on a vertical plane as shown in drawing on the left. The vertical plane is above the burner present, where a combustible board is positioned. The combustible board is exposed to a burner flame, which generates a combustion pattern, which represents the flame shape as shown in the picture on the right. Which method is used to characterize the flame shape? The procedure is shown here in 3 steps. Step 1, a grid is marked on the wooden board for flame shape characterization as shown on the left. Step 2, the board is now vertically positioned on top of the burner at the center line, so the burner flame can work unhindered on both sides of the board. Step 3, the combustion pattern on the board needs to be digitized, which finally represents the flame envelope for further evaluation and comparison. I want to explain a bit more about the evaluation of the flame shape. Here is the flame envelope and the limiting profile as defined in the 2nd edition of the EN 54399. The plot on the left shows the limiting profile based on the coordinates with X-Y axis according to standard. An outer flame envelope is described in which the overall measured flame shape must lie, as well a range in which the flame tip should be located, here marked in green. The flame tip has to be lie above the minimum accepted line. 2 examples on the right should demonstrate how a flame combustion pattern fits into the envelope. One example shows a well-acceptable combustion pattern with the flame tip inside the green market range. Another example should demonstrate a short combustion pattern with a flame tip below the minimum accepted line. It is allowed to adjust the flame shape if it's necessary by change of the gas mixture, but within the tolerance range. The method is described in the standard, but this is only informative. These are some examples of different flame shapes that we have observed in our lab and other labs we work with. The flame shape can vary in labs as seen in this plot. We have to notice very long flame shape as well very short flame shapes. Some of the flame shapes appear to be close to the limiting profile, and some of them lie out of the accepted envelope, all through the condition of the parameter settings that generating a flame shape are well defined in the standard. So the question is, where does the flame shape variation come from? The flame shape is mainly determined by the burner design and the gas mixture, whereby the gas supply system, like the gas pipes and mass flow controller for propane and air, can also play a role. It is assumed that these 3 factors influence the flame shape that could lead to flame shape variation, as seen in this plot. Therefore, one of the next steps was to investigate parameter settings for burner and gas mixture in order to better understand the impact on the flame shape. Let's have a look at the parameter settings that can influence the flame shape, starting with the burner design. The standard recommend is suitable ribbon burner from supplier AGF. The drawing on the left shows the configuration of a burner with a Venturi mixture and the general burner dimensions. The drawing in the middle shows the arrangement of burner holes with the number of holes, the nominal hole diameter, which is 1.32 millimeter, as well as the tolerance range. Typical for the AGF burner are so-called pilot holes, which are located above and below the center holes, as shown in the picture on the right below. The flame from the pilot holes support the flame from the main center holes, which improve the flame stability. Different types of burner were tested. and the impact on the flame shape was determined. We used a homemade fishtail burner without pilot holes and compared with standard AGF burner, as the picture from the burner should demonstrate. In the plot on the right, it is shown that the homemade burner design generates significant different flame shape, presented in a red line. In this case, the shape layout of the accepted envelope, given with the dotted line here. For comparison reason, a typical flame shape of an AGF burner is added into the plot, the blue line. This example should demonstrate that different burner design could cause flame shape variations. This can result in flame shape outside the accepted envelope. So far, different burner types are not excluded, but with the new standard version, the use of alternative burner designs or a homemade burner is forbidden. The influence of the burner hole diameter on flame shape was investigated. The plot on the left shows an estimation of the gas flow velocity as a function of the hole diameter, taking into account a constant gas mass flow. The plot shows the selected range of hole diameter between 0.6 and 2 mm on the y-axis, the total cross-sectional area of the center holes and pilot holes in the second x-axis on right, and the calculated velocity on x-axis on left. As expected, the gas flow velocity decreased with larger hole diameter and increase as the hole diameter becomes smaller. 3 burners with different hole diameter were selected for this estimation to determine the flame shape, marked with a red circle. The plot on the right showed that all flame shapes are within the accepted envelope, even with a larger burner hole of 1.8 mm, but except of a burner with a very small hole diameter of 0.9 mm, presented in red line, which is outside the accepted envelope. It is very unlikely that the burner holes are deviating so much from the given standard tolerance range between 1.3 and 1.4 mm. Therefore, the flame shape is almost unchanged when the hole diameter is within the tolerance range, provided the pilot holes are present. The flame shape should be comparable in labs if identical burner is used under the same condition according to the standard. Another parameter is the gas mixture shown here. It is assumed that deviation in the gas supply could be a reason for flame shape variations. The gas flow rates are well defined in the standard, including a tolerance range for propane and air, as listed on the left. We investigated the impact of different gas flow rates, taking the standard tolerance range into account. For this purpose, the limit values of the gas flow rates at the upper and lower tolerance was applied and compared with nominal setting. The plot on the left shows changes in the gas flow rates within the defined tolerance have only minor impact on the flame shape. All flame shape live within the accepted envelope as seen in the plot. In a further approach, it is assumed that an incorrect burner air supply could have a stronger influence on the flame shape and causing variation based on own experience we had with a malfunction of a mass flow controller. The burner air was much higher of 40%, about 2,250 milligram per second air, but was not detected over a long time until the next calibration of mass flow controller was done in our lab. Therefore, experiments with very low and very high air supply were made. It is obvious that the flame shape can significantly change if burner airflow is outside the tolerance range, as shown in the plot on the right in red line, which also could result in flame shape out of the accepted envelope. It seems plausible that the deviation in the gas supply can influence the flame shape. So far, I have demonstrated how the parameter setting can change the flame shape. The following slides should show how parameter setting that change the flame shape impact the flame spread results. It seems that a homemade burner can lead to different flame spreads. The plot shows the flame spread from the experiment is slightly lower of approximately 0.1 meter compared to average flame spread in our lab. A similar effect can be seen when using a burner with a small hole diameter of 0.9 millimeter. The flame spread is also reduced by approximately 0.1 meter. What we have learned from this experiment is that the flame spread can change if a non-standard burner is used or the hole diameter of the burner is below minimum tolerance. For example, if the holes are blocked by soot or ash deposit like this. This could also lead to lower flame spread results. The flame shape can vary due to change of gas mixture, as we have seen before. Does this impact the flame spread? In this case, a gas mixture was selected with the maximum airflow rate on one side and the minimum propane flow rate on the other side, according to allowed standard tolerances. The results of flame spread by selecting gas mixture is slightly lower of about 0.1 meter again, compared with the flame spread at nominal parameter setting, as seen in the plot. This should demonstrate that the flame spread can slightly vary due to the change of gas mixture within the tolerance range. So far, we have not found parameter setting within the allowed tolerance range which have led to flame shapes out of the accepted envelope with remarkable influence on the flame spread. Further investigation should explain a correlation between a short flame shape and a low flame spread. For this purpose, 3 different flame shapes has been selected, as shown in the plot on the left, marked in red line. With this experiment, 2 flame shapes are borderline, named Lab 1 and Lab 2, with the flame envelope close to the minimum accepted line. 1 flame shape, named Lab 3, is below the minimum accepted line, therefore outside the limiting profile. A typical flame shape is added in the plot for comparison, represented in the blue line. Next experiments were performed to demonstrate that a short flame shape can be reproduced in our lab by adjusting the parameter of the gas mixture, which is shown in the table on the right top. In this case, the gas mixture was modified until the adjusted flame shape fit nicely to the short flame shape we have selected. The plot in the center shows the reproduced flame shape of Lab 1 and Lab 2 with a dotted line compared to the selected short flame in solid line. We were able to reproduce the flame shape quite good. The propane gas flow, which was needed for the reproduction of flame shape Lab 3, is remarkably low at 300 milligrams per second out of the nominal gas settings. However, the flame shape of Lab 3 was not further adjusted to fully meet the selected short flame shape, as shown in the right plot. What we have seen is that a significant short flame shape can be reproduced in experiments if the gas flow rate are outside of the tolerance range. So how does a reproduced short flame shape impact the flame spread results? The plot shows the flame spread results of a reproduced flame compared to original results. As shown in the plot, the flame spread could be nicely reproduced, except the flame spread of Lab 3, because the gas mixture was not further adjusted as mentioned in the slide before. However, this is a strong indicator that the parameter of gas mixture could deviate from standard settings. This is one example where the correlation between a short flame and some failure in experimental parameter settings could be proven. The results also confirm that significant flame spread variation cannot be explained by variation of parameter setting in the gas mixture within the standard tolerance range. So I would give an example about the monitoring of the burner flame output. The control and the record of the burner flame output is mandatory and have to be done before start testing. It's the so-called daily check. This plot represents the flame output of 20.5 kW burner flame under nominal parameter settings, measured on the heat release rate as a function of time, present in a black line. The daily check confirmed the correct flame output within the tolerance range. The reproduced gas flow from the experiment lab 3 result in a flame output of approximately 15 kW, which is outside the tolerance range. Deviation in the gas supply can be detected very well in the daily check as demonstrated with this example. In case of deviation, corrective measurement can be taken. Yeah, I'm coming to the conclusion. It could be shown that the flame shape can impact the flame spread results. It has been demonstrated that the flame shape variation within the allowed limits given by the standard EN 5399 only have negligible impact on the flame spread. Significant flame shape variation can be correlated to deviation from the standard conditions. It was demonstrated that selected too short flame shapes result in low flame spread. Therefore, it's important to check the flame output according to the EN 50399 in order to detect deviation at a very early stage. The applied method for the characterization of burner according to the EN 50399 by using a wooden board is practicable and can be an indicator for changes in the burner flame test condition. This method should become mandatory for all test laboratories. Yeah, that's the end of today's presentation. Thank you very much for your attention. And also, I would like to thank the team who contributed to the content of this presentation. Thanks a lot.
Excellent presentation, Thomas. And again, very, very important information as we all try to develop and have good fire safe products in the marketplace. It's good to understand this as we develop materials and cable designs. I want to ask if any of our participants have any questions. Hopefully you can enter those and type those in the chat function. Currently, I don't see any questions. And again, it was a very good presentation, very clear. But we'll give you a moment here. If you have any questions at all, please enter them in the chat function and we'll ask them to Thomas. So Thomas, question I have is, obviously there are a number of different horizontal and vertical flame tests for cables. Can you make a general assumption that the same concepts for flame shape will and the intensity of the flame also will affect results or the consistency of the test? In other types of methods other than 50399.
Yep, Dave. What means? I mean, the 50399 is the standard test method we have to use. So, can you just repeat? I mean, what is the
Yeah,
what
I'm
other
just
test method?
trying to see if there's any correlation to this data and flame shape that you observe. Based on burner and intensity, can that be applied to some of the other fire testing for cables, other methods?
Well, I mean, in general, I mean, yes, but when we speak about flame spread, let's say that's a vertical flame spread. Other methods are like horizontal, you mentioned. This is a completely different test method. It's
yes.
not cannot be correlate. I mean, to this method, which is typical used the plenum like in the US. So that's a different test method.
Sure. Okay, are there efforts to verify correct flame shapes at different labs to ensure repeatable results?
No, I think it's to me it's quite important that if the new standard is published, so that laboratories will be following this method. The method is informative, but I would strongly recommend to do it, and not just one times per year. I would recommend to use the method. If any changes or like maintenance or change in the gas supply or whatever, burner cleaning, calibration stuff like this, this method should be definitely used to get more evidence in the flame shape variations. I mean, every laboratory should gather its own experience by using the method. The method itself maybe is not perfect, but this method helps definitely to understand deviation. And I mean, in this way, strong deviation can be identified. So, and one comment maybe on this, we are working internally to improve and simplify the procedure for flame characterization based on the analysis of thermographic picture. This was presented in the IWCS last year by Dr. Waldemar Stöcklein. So, but in general, it's strong recommend to start and to use this method to get a clear understanding and about the flame shape, and to really understand deviation.
Yeah, and I think to try to minimize those deviations from laboratory to laboratory is always important. And so hopefully various round robin testing or effects at different laboratories can use this procedure or others to make sure we get consistent results.
Yes, that's true.
Yep. Thomas, can regional differences in gas supply cause variations?
If the gas supply, I mean, if there are some defects in the gas supply, I mean the pipes, for example, then sure this can impact the flame shape, and that's the reason why we need to somehow control this. Yeah.
Could it be that the thermal content of the gas, is that variable or is that fairly consistent?
Should be consistent. Let's say as far the flow, the mass flow is the same according to the standard setting parameter. I would not expect here any deviations. So what we have seen is by playing with or changing the mixture within the tolerance ranges, sure this will be slightly change the flame shape, but this is not significant and just a little bit impact the flame spread as we have proven by roughly 0.1 meter. I mean, this is a slight improvement, but it's not significant.
In slide 13, if you want to go to slide 13, it was hard to see the difference between the two red lines, 500 milligrams per second and 3,500 milligrams per second. Can you please describe which was which?
So slide 13, we are here, right? So, and the question is?
The difference between the two red lines. You know, which is which, the 500 milligrams per second or the 3,500 milligrams per second?
Okay. So the 500 is the left one, which is, you see, more vertical, and the opposite is the 3,500 milligram, which is a significant more or higher air supply. So this is the difference between. So the key is the air supply. So, and if the air supply, the problem in air supply is that the air supply itself does not contribute to the flame out, to the power of the flame, just contributing to the flame shape, and this is affecting finally the flame spread. A very vertical flame shape, as seen here in this plot, reduce the flame spread as well. A very strong oriented, more horizontal oriented flame shape like this one here is also reducing the flame spread results, because the flame is passing the cable, pushing through the cable surface, which reduce the heat amount on the cable surface, and that's the reason why the flame spread is a little bit lower then. So that is, and once again, if just the air is not correct by any leakage, for example, this cannot be checked by the daily check. When I say you need to control the power of the flame, because here just the propane contributing to the power of the flame, not the air.
Good. In your opinion, which are the other important parameters that could affect the test?
Oh, this is broad.
Yeah.
Yeah, broad, because I mean there is a lot of different parameters. So one key parameter is related to the air flow through the chamber, and there's a number of parameters which can affect the overall airflow and air distribution in a chamber, like the air which is fed to the chamber, like the extraction air, like chamber builds inside, like leakage and so on. There's a number of parameters which also can have effect on or impact the flame spread results, finally the burn test results. So there was a number of investigations done in the past and also published in different papers over the last year. So,
and we've seen, you know, temperature and humidity and airflow and barometric pressure and all sorts of things can affect these tests.
Exactly. So the general comment would be here, or the recommendation, the standards, it's very precise and very complex. All the parameters which are defined in the standard need to be kept under control.
And with that, standard burners is mandatory. Isn't that correct? I mean, you have to have a standard burner, not a handmade type burner.
That's right. But the new edition, definitely the burners very precise, described and to use this AGF burner. So that means looking forward, any deviation from this burner, at least in the future, should be not anymore present. In the past, maybe there are some variation, but not in the future, I guess.
Good. Anything we can do to make them more consistent will be a good thing.
Yeah.
How many different types of cable designs have you evaluated in your study, and is there a similar trend for the variation applied to different designs or thicknesses of materials?
Yeah, there's two different things. So first, we speak about the repeatability of test results. We always use this reference cable at the beginning from 2016, which is which is let's say, it's needed to really understand the performance of any parameter we have investigated. So if the question is, and so using the reference cable, which is also described in the standard. So using this reference, you get a good understanding about the impact of individual parameter. And when we speak about cable design, I mean, there's a huge number of different cable designs. So, and this is not finally proven yet, but it's in general, I can say that the cable design itself can also perform different, which means the data scattering by a certain cable design could be different from cable design to cable design. So when we speak about the variance, the sigma. So for the reference cable, we have a very precise data and understanding what a sigma is, but we cannot transfer the results to any other cable design in general. So this is then you need to repeat the test with a certain cable design you want to understand to get here statistical evidence about the scattering, let's say, data when we speak about the flame spread, for example.
Right.
So the question, the answer is when we have an understanding with the reference cable, we cannot tell this is the same variance in any other cable design. This need to be investigated carefully.
Two more questions. Inconsistent flame shape can impact the results, obviously. We've talked about that. Do you burn a wooden grid as a rough verification of the flame envelope, or do you just verify through the gas air supply using a flow meter?
So if I correctly understand the flow, the gas or air flow, it's we do not use a flow meter. We have so-called the mass flow controller, MFC. So which is very precise equipment to ensure that the flow, the mass flow is always constant.
Okay. And last question. It appears that the flame shape was profiled from the center of the burner. Have you checked the flame shape from the edges of the burner? And have you studied the variation of the flame shape along the burner caused any difference in the burn results?
Sure, so the flame shape at the edge. I mean, when the method is the wooden board is in the center of the burner. When you move from the center to the edge, left or right, so then you get a different combustion pattern, which is normal, let's say, because in the center, that's the reason the center is taken. The heat is symmetrical distributed. I mean, you on the left and right. When you go more to the side, at the end, the heat is reduced, which is the normal behavior. So I mean the flame shape on the side of the flame is different than in the center. So the decision is to be focused on the center and not to any other flame or beside the center. So this is different flame combustion pattern and flame shape you will see on the digitized envelope.
Very good. Well, a lot of excellent questions, and we certainly thank your participation to ask those questions of Thomas. Again, thank you so very much, Thomas, for an excellent presentation and all those good answers and your perspectives to those questions. Please note the contact points being shown on your screen should you wish to contact Thomas after today's event. Each of these IWCS webinar series presentations are recorded and will be archived on the IWCS.org website. Normally takes maybe a week or so to have these put up on the site, so you can watch it again or share the presentation with your colleagues as well. The IWCS webinar series will conduct technical paper presentation webinars as well as sponsored company events several times each month. Our next scheduled technical paper presentation webinar event will be on Friday, August the 19th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event. Please feel free to share our announcements with your colleagues so that they can join and register as well. Before we conclude, any last minute questions from the audience? Hearing none, it's important that we recognize and thank our IWCS partner sponsors who greatly contribute to the success of the Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you and our global community. Again, thank you to these leading suppliers in our industry for your support. And you can see that Corning and Thomas's colleagues are also very strong contributors to IWCS. For over 70 years, the IWCS Cable and Connectivity Industry Forum has been the recognized leader in showcasing new technologies in cable and connectivity products, processes, and applications. And with strong perseverance and confidence, our next 71st annual Cable and Connectivity Industry Forum will take place live and in person on Monday through Thursday, October 10th through the 13th, 2022, at the Rhode Island Convention Center in Providence, Rhode Island, USA. Please watch your inbox, your social media, and our website to learn more about the exciting information as it becomes available. We're in the process of finalizing registration and the program, so that information will be coming to you very, very shortly. So please visit our website at IWCS.org for more event details. So with that, thank you for participating, and this concludes today's webinar event.